The idea that the atomic blueprint seeks to unify how we understand every atomic process under one consistent scientific framework carries a deeper meaning than it first appears. It suggests that the natural world, especially at the atomic level, is not a collection of unrelated events, but a harmonious system governed by interconnected rules. When scientists examine atoms, they often use different models depending on the situation. Sometimes the atom behaves like a particle, sometimes like a wave, and sometimes it behaves in ways that appear unpredictable. This variety of behaviors can make the atomic world look fragmented. The keynote argues that this fragmentation is not a property of nature, but a result of how we try to describe it. In reality, all atomic processes from the movement of electrons to the bonding of atoms follow a single, coherent framework, even if our interpretations differ. This keynote emphasizes the need for a unified perspective that can bring together all these behaviors under one scientific language. Instead of switching between classical rules and quantum rules, a consistent framework would allow us to interpret atomic events without contradiction. For example, when electrons jump between energy levels, light is emitted in the form of photons. Classical physics explains the motion of particles, but cannot fully explain the sudden jump. Quantum physics explains the jump, but often removes the intuitive idea of continuous motion. A consistent blueprint would connect these views, showing that the behavior is not contradictory, but simply different expressions of one underlying set of principles. This idea also helps deal with the confusion created by uncertainty in quantum mechanics. Many people misunderstand uncertainty as randomness, as if atoms behave without rules. But uncertainty is actually part of the system's design, not an exception. A unified atomic blueprint portrays uncertainty as a controlled, mathematically defined feature of atomic behavior. Instead of thinking of atoms as unpredictable, we begin to see them as following laws that include probability as an essential component. This view gives us a clearer, more complete understanding of how the atomic world operates. When all atomic processes are understood through one consistent model, our interpretations become more powerful. Scientists no longer need to shift models or use different explanations for similar events. It becomes easier to predict how atoms will respond in new environments, how they interact with energy, and how they combine to form materials. This unified understanding also strengthens technological innovation, because technologies like lasers, solar cells, and semiconductors depend on precise control of atomic behavior. A consistent blueprint allows us to improve these technologies by giving us a more reliable mental map of how atoms respond to forces, fields, and energy changes. Ultimately, this keynote highlights that the atomic world is not chaotic or divided. It is structured, interconnected, and governed by a deep coherence. The blueprint shows that all atomic events flow from the same foundation. Understanding that foundation brings clarity to science, stability to theories, and confidence to discoveries. The idea that atoms behave according to patterns that repeat across all elements and interactions reveals something fundamental about the nature of matter. At first glance, atoms seem incredibly diverse. Hydrogen behaves differently from oxygen, and metals act differently from gases. Yet beneath these differences lies a powerful uniformity. The rules that govern how electrons move, how energy is absorbed or released, and how particles interact show a repeating pattern across the entire periodic table. This keynote emphasizes that despite the enormous variety of materials and reactions, the atomic world operates on a set of principles that remain constant. Consider the structure of atoms. Every atom, regardless of its size, follows the same basic arrangement: a nucleus surrounded by electrons. The number of protons may change, the electron shells may increase, but the overall architecture repeats. This repetition is not limited to structure. It extends to behavior. When an atom absorbs energy, its electrons shift to higher energy states. When the energy is released, electrons fall back and emit light. This same process occurs in small atoms like helium and large atoms like uranium. The pattern is universal, and it is this universality that makes science predictable and powerful. Chemical bonding also reflects repeating patterns. Atoms form bonds based on their need to achieve stable electron configurations. Whether it is covalent bonding in water molecules or metallic bonding in iron, the underlying principle is the same. Atoms share or trance for electrons to reach stability. This predictable pattern is why chemistry can explain millions of reactions using a relatively small set of rules. Even the shapes of molecules follow patterns determined by electron repulsion and quantum mechanics. This consistency allows scientists to forecast the behavior of materials long before experimenting with them. The periodic table itself is a perfect demonstration of repeating atomic patterns. Every row and column represents recurring behavior. Elements in the same group react similarly because they share the same number of valence electrons. Sodium reacts explosively with water, and potassium does too, not by coincidence, but because both follow the same atomic rules. These repeating tendencies allow scientists to place new elements into the table and immediately predict their characteristics. This keynote also connects to the quantum world, where electrons and particles follow mathematical patterns that repeat across all atoms. Wave functions, energy quantization, spin, and probability distributions behave consistently no matter what element is being examined. Even though quantum behavior may appear strange, it remains regular and predictable within its own rules. The repetition seen in atomic interactions is a direct reflection of these deeper quantum patterns. By recognizing these repeating behaviors, we gain the ability to simplify complex systems. Instead of treating each element as unique, we understand them as variations of a shared template. This unified view gives scientists the tools to design materials, understand biological processes, predict chemical reactions, and create new technologies. The repeating patterns in atomic behavior reveal that the complexity of matter is built from a beautifully simple and consistent foundation, and it is this foundation that makes the scientific study of atoms both reliable and profoundly meaningful. The idea that the atomic blueprint highlights the balance between predictability and uncertainty within atomic behavior brings us into one of the deepest truths of modern science. Atoms do not behave in a completely predictable way like classical objects, nor are they entirely random. Instead, they exist in a space between these two extremes, where order and uncertainty coexist in a delicate balance. This keynote shows that the atomic world is governed by laws that define how particles tend to behave, while still allowing a degree of uncertainty that is built into the structure of nature. In classical physics, an object's future can be predicted perfectly if we know its position and motion. But atoms do not work like that. Electrons, for example, do not orbit the nucleus in neat paths like planets around the Sun. Instead, they exist in regions of probability called orbitals. We cannot say exactly where an electron is at any given moment, but we can predict the likelihood of finding it in a certain area. This is the heart of quantum uncertainty. Even though the outcome is not precisely determined, the probabilities follow strict mathematical rules. So uncertainty is not the absence of order. It is a different kind of order, one that blends predictability with indeterminacy. This balance becomes clearer when we consider energy levels in atoms. Electrons cannot occupy just any energy state. They are restricted to specific levels, meaning their behavior is quantized and predictable. Yet, when an electron transitions between levels, the exact moment of the jump cannot be predicted. We can describe the energy released, the pattern of spectral lines, and the overall behavior, but we cannot say exactly when any single event will occur. This mixture of fixed rules and unpredictable timing is a perfect example of atomic balance. Another illustration is the way atoms interact with light. The absorption and emission of photons follow precise laws that allow scientists to map atomic structures with extraordinary accuracy. Yet each interaction carries uncertainties in direction, timing, and outcome. Such uncertainty does not weaken the scientific framework. It strengthens it by revealing the probabilistic nature of atomic behavior. The atomic blueprint shows that these probabilities are not random noise, but essential characteristics that help atoms maintain stability and coherence. Even chemical reactions demonstrate this balance. The general pathways are predictable, and scientists can determine how atoms will bond, how much energy will be released, and what products will form. But the microscopic details, such as which exact atoms collide first or the precise moment a bond forms, remain uncertain. This uncertainty, however, does not prevent chemistry from being one of the most precise sciences. Instead, it reveals that atomic interactions follow patterns while allowing small variations. Understanding this keynote allows us to appreciate the true elegance of atomic behavior. Atoms do not obey strict determinism, nor do they drift aimlessly. They follow a blueprint that integrates firm rules with flexible outcomes. This balance is what allows atoms to form stable matter, participate in dynamic reactions, and create the foundation for everything we observe in the universe. The idea that particles follow universal principles, even when their outcomes appear probabilistic, is a reminder that the atomic world is far more organized than it first seems. When people hear that atomic events are probabilistic, they often imagine randomness or unpredictability without reason. But in reality, atomic particles, electrons, photons, protons, and others operate according to precise mathematical laws. These laws apply everywhere in the universe, from the atoms in our bodies to the atoms in distant stars. Even when the exact outcome of a single event cannot be predicted, the overall behavior follows patterns that never break. This keynote shows that probability is not chaos. It is a structured form of order. At the quantum level, particles behave in ways that do not fit the classical picture of straight line motion or fixed positions. For example, an electron can act like a wave and spread across space, or behave like a particle and appear at a single point when measured. This dual behavior may appear contradictory, but it still follows universal principles like wave functions, quantization of energy, and conservation laws. The electron's actions are not random choices. They are consequences of the laws that govern all quantum particles. The probabilistic nature of these actions emerges from the wave function, which precisely defines the likelihood of each outcome. So even the uncertainty follows a rule. Another clear example is radioactive decay. We cannot predict the exact moment when a particular atom will decay, but we can predict very accurately how many atoms in a large sample will decay within a certain time. This is possible because each atom follows the same decay law. even though the timing is probabilistic. The underlying principle remains fixed. The decay rate is constant for that substance. This means thousands of unpredictable microscopic events still produce a stable, predictable macroscopic pattern. The uncertainty of individual events does not erase the unity of the principle behind them. Even more complex interactions, such as the scattering of electrons or the tunneling of particles through barriers, demonstrate universal patterns. Quantum tunneling may seem mysterious particles passing through barriers they should not be able to cross, but it adheres to strict rules described by quantum mechanics. Every electron, everywhere in the universe, follows the same tunneling equation. The outcome for a single particle may be uncertain, but the probability of tunneling is perfectly defined by the law. This keynote also applies to atomic collisions, chemical reactions, and energy transitions. When atoms interact, they do so according to principles like conservation of energy, symmetry, and quantized states. These rules hold in every reaction, in every environment, and under every condition. The specific results may vary, but the framework never changes. This universal consistency allows scientists to build models, design experiments, and create technologies with confidence. Understanding this keynote shifts the way we view the atomic world. Instead of imagining quantum events as random mysteries, we see them as expressions of deeper, universal laws. The probabilistic nature of particles is simply a different mode of order, an order that allows flexibility without losing consistency. This blend of uncertainty and universality is what makes atomic behavior both fascinating and profoundly reliable. The idea that the atomic blueprint bridges classical intuition with quantum rules and helps us interpret complex atomic actions more clearly highlights a major challenge in science: making sense of a world that does not behave according to everyday experience. Classical physics, based on the laws of motion, force, and energy, gives us an intuitive understanding of objects we can see and touch. It explains why a ball falls, why a car accelerates, and why a pendulum swings. But at the atomic level, these familiar rules begin to break down, and a new set of principles, quantum mechanics, takes over. The problem is that quantum behavior often seems strange, abstract, or disconnected from the world we observe. This keynote emphasizes the importance of building a conceptual bridge between classical thinking and quantum logic, so that the atomic world becomes easier to understand. At the classical level, objects have definite positions and follow predictable paths, but electrons do not orbit like planets. They exist in clouds of probability, and their properties change when observed. Classical intuition does not naturally fit this behavior. The atomic blueprint helps by connecting the classical ideas we understand, such as energy, motion, and interaction, to their quantum equivalents. For example, classical physics tells us that objects have specific amounts of energy, while quantum physics introduces the idea of quantized energy levels. By linking these two viewpoints, the blueprint shows how electrons still follow energy rules, but do so in discrete steps rather than continuous values. This connection helps make quantum ideas less alien. Another example of this bridging role is the wave-particle duality. Classical thinking separates waves and particles into two different categories, but quantum mechanics shows that particles can behave like both. The blueprint helps us reinterpret this duality not as a contradiction, but as a more complete description of nature. A particle is not sometimes a wave and sometimes a particle. Rather, it possesses characteristics of both, and how we observe it determines which aspect becomes visible. This interpretation softens the gap between classical expectations and quantum behavior. The atomic blueprint also helps clarify interactions such as bonding, scattering, and energy exchange. In classical terms, atoms bond because forces pull them together. In quantum terms, bonding involves shared electron clouds, overlapping wave functions, and energy minima. When these ideas are linked together, the process becomes more understandable. Instead of abandoning classical reasoning, the blueprint refines it, showing that classical concepts are approximations of deeper quantum principles. This bridging framework becomes especially useful in technology. Devices like lasers, semiconductors, and MRI machines operate entirely on quantum processes. Yet they must be designed using models that engineers can understand and apply. The atomic blueprint provides that connection, allowing people to predict outcomes using quantum rules while still relying on classical intuition for interpretation. It transforms quantum mechanics from an abstract theory into a practical tool. Ultimately, this keynote expresses the importance of unity in scientific understanding. The atomic world does not require us to reject classical ideas. It requires us to expand them. By linking classical intuition with quantum laws, the atomic blueprint offers a clearer, more complete picture of how atoms behave, enabling us to interpret complex interactions with confidence and clarity. The idea that measurement, energy states, and particle interactions must be explained using the same coherent logic highlights the need for unity in the way we understand atomic behavior. In many explanations of atomic science, these concepts are often discussed separately. Measurement is treated as a strange quantum event. Energy states are described through mathematical levels, and particle interactions are explained using different sets of rules. This separation can make the atomic world feel fragmented or inconsistent. The keynote emphasizes that all these processes are connected and should be interpreted through one consistent framework. When we view them through the same logic, the atomic world becomes more organized and understandable. Measurement is one of the most puzzling aspects of quantum physics. When we measure a particle, its possible states collapse into a definite result. This behavior seems different from how energy levels change or how atoms interact, but in reality, they are connected through the principles of quantum mechanics. Measurement does not introduce new rules. It simply reveals one outcome from a set of possibilities defined by the same underlying wave function that governs the particle's behavior in all situations. The measurement process follows the same mathematical patterns that describe motion, energy distribution, and interaction. Instead of seeing it as a special event, the blueprint encourages us to view measurement as part of a continuous system. Energy states are another essential element that must fit into this consistent logic. Atoms have specific energy levels that electrons can occupy, and transitions between these levels occur in quantized steps. These energy states are not separate from measurement or interactions. They are part of the same quantum structure. When an electron absorbs a photon, it gains the exact energy needed to move to a higher level. When it drops back down, it releases energy as light. These transitions follow strict rules, the same rules that determine the probabilities of measurement outcomes. By connecting these ideas, we see that energy states are not isolated concepts. They are shaped by the same underlying quantum logic that controls everything else. Particle interactions also depend on this unified framework. When two atoms collide, share electrons, or exchange forces, their behavior follows the same equations that describe energy levels and measurement probabilities. The interactions are governed by the wave functions of the particles. the conservation of energy, and the symmetries of the system. Every exchange of energy or momentum fits into the same mathematical structure. This unity allows scientists to predict how particles will behave in a variety of situations using one coherent set of principles. Seeing measurement, energy states, and interactions as separate can create confusion, but understanding them through one consistent framework reveals a deeper order. All atomic processes, no matter how different they seem, emerge from the same foundation. The atomic blueprint reminds us that the universe does not operate with separate rule books for different events. Everything, from observing an electron to bonding two atoms, follows the same coherent logic. This unified approach strengthens our understanding of the atomic world and makes its behavior clearer, more predictable, and more meaningful. The idea that a consistent atomic blueprint strengthens our understanding of nature by giving a stable foundation for analyzing chemical reactions, atomic transitions, and quantum events emphasizes the importance of having one unified way to interpret all atomic behavior. When scientists attempt to explain atoms using scattered models or separate theories, the picture becomes confusing. But when there is a stable, reliable framework that works for every atomic situation, our understanding becomes clearer, deeper, and far more accurate. This keynote shows that a single foundational approach allows us to connect the smallest quantum events to the largest chemical processes without contradiction or uncertainty in interpretation. Chemical reactions, for example, involve atoms rearranging and forming new bonds. At first glance, these reactions can appear messy or unpredictable, with countless collisions and exchanges happening at microscopic scales. But the atomic blueprint reveals that all these actions follow the same underlying principles: electron distribution, energy levels, and quantum probability. When we look at a reaction through this unified lens, its behavior becomes logical rather than chaotic. We understand why atoms combine in specific ways, why certain reactions release energy, and why others require energy to proceed. This consistency allows chemists to design reactions, predict outcomes, and create new materials with precision. Atomic transitions also become clearer within this stable framework. When an electron moves from one energy level to another, it is not acting randomly. It is following quantized rules that apply to every atom in the universe. The wavelengths of light emitted during these transitions form the spectral lines that scientists use to identify elements in distant stars. The atomic blueprint shows that these transitions always follow the same principles of quantization, conservation of energy, and probability. With a unified foundation, we can explain not only why an individual atom emits a photon, but also why entire galaxies show consistent patterns of atomic behavior. The same rules apply everywhere, giving us confidence in our interpretations. Quantum events, which often seem strange or unintuitive, also become easier to understand with a stable foundation. Quantum tunneling, entanglement, and superposition are not disconnected mysteries. They are expressions of the same underlying atomic logic. When these processes are viewed as part of one coherent system, their behavior becomes more predictable and meaningful. Instead of appearing as exceptions to the rules, they become natural consequences of the blueprint that governs all atomic processes. This unified view helps scientists build technologies like quantum computers, lasers, and medical imaging devices with far greater clarity. A stable atomic foundation also strengthens scientific reasoning as a whole. When all atomic phenomena are understood through a consistent blueprint, scientists no longer have to switch between contradictory explanations. They can interpret results with confidence, knowing that the underlying principles do not shift from one situation to another. This stability is what allows science to build knowledge layer by layer, creating accurate theories, reliable technologies, and deeper insights into the nature of the universe. Ultimately, this keynote shows that the atomic blueprint is not just a theoretical concept. It is the backbone of our understanding of matter itself. By providing one coherent foundation, it allows every chemical reaction, every atomic transition, and every quantum event to be understood within a single, dependable framework, bringing unity to the complexity of the atomic world.